the stream. So welcome back to the afternoon session of IGS2 2022. My name is Matthias Staudacher from Humboldt University Berlin. I'll be chairing this the next 3 talks. For the first talk, I actually have a slight conflict of interest, as you will see in a second. So that means that you're only allowed to ask nice questions after this talk. Anyway, so we have Changrim Ahn from Eva Women's University in Seoul, who will be talking about some connection between so-called Pólya formula and Jordan blocks in spin chains.
Thank you. Of course, first of all, I want to thank organizers for kind invitation. So as I introduced, I'll talk about Jordan block, which is quite rather conflicting with the integrability. And what I'm going to say today is basically that standard integrability technique sometimes are not enough to solve the integral models. This talk is based on 3 papers as a result of a wonderful collaboration with Matthias, of course, in our chair, and Luke Corcoran. I'm not sure whether he's around. In the first work, we basically found that certain integrable spin chain model has a very rich Jordan block spectrum, which can be only discovered by some kind of phenomenological way. And we applied, which I'm going to explain, the standard technique of integrability to explain those, but failed. And in our second work, which is the main part of this talk, is that we changed our strategy from using integrability to using some kind of a mathematical technique like combinatorics or linear algebra, etc., to find out the so-called Jordan, this rich Jordan block spectrum, which we succeeded. And in third work, we improved some case which is quite generic, which you will see that some generic number of the field contents into certain very beautiful formula based on Pólya. Why it is in the name. His name appears in the title. Okay, the story begins in the so-called fishnet model, where many of you, several talks already has been given today or yesterday, where all these authors introduced this, the coupling constant goes to general limit, while these 3 deformation parameter goes to imaginary infinite, such that certain combination can be finite. There are several different choices, but I'm going to focus on some the cases where Q's goes to infinite, such that G goes to general limit times this infinite has a finite value. Then this fishnet model, or generalized fishnet model, where fishnet model is usually including only 1 parameter, and generalized fishnet model has 3 these parameters, has this kind of Lagrangian. And shortly after, these authors, including Matthias here, studied the spectral problem of this super-Yang-Mills, kind of super-Yang-Mills theory. And since G goes to general limit, 1 loop is usually enough. And the dilatation operator is described by certain specific spin chain model, which they named eclectic. I don't know why, personally, but anyway, that's the name I adopt. And it is just given by some kind of a chiral permutation operator. So since we are considering this 3 scalar sector of the super-Yang-Mills theory, I'm just trying to say for short notation that instead of this pi 1, pi 2, pi 3, I'll just denote the number 1, 2, 3. And then since we are dealing with the single trace operator, which should be cyclic, so we should consider certain combination of 1, 2, 3s in cyclic form. Okay, when I say cyclic, well, sometimes I'm going to omit it. It's basically summation of all possible the cyclic rotations. And this chiral permutation operator is acting on certain special case where, say, this P21 acts only when it sees 2 and 1 together, and it changes 2 with 1. When it acts on 1, 2, it just kills it. That's why difference from the usual permutation operator. P13 and P32 is similar. And this seems a very simple spin chain model, which is, of course, non-Hermitian, though. It's integrable because it can be constructed from the so-called R matrix, 9 by 9 R matrix, which satisfies Yang-Baxter equation. And one can construct the monodromy matrix and transform matrix, etc. And thanks to the Yang-Baxter equation, this transform matrix commutes. And there will be infinite number of conserved charges. One of them, most important, is Hamiltonian, which is the logarithmic derivative of transform matrix with u to be 0. Or the more simple case is just a set u to be 0, which is actually nothing but shift operator. Yeah, so P1, 2, 1, x1, 1, 2 is 0. It's simply 0. It kills it. So if instead of 2, 1, if this operator acting on 1, 2 state, it's 0. So, well, one can try first of all this standard, say, algebraic Bethe ansatz, since it's integrable. So, since we already constructed the monodromy matrix, one can try to apply this commutation relation, so-called fundamental commutation relation, to find the eigenvectors. But for example, if you write down this commutation relation for some simple cases, actually it looks like this. So here the R component is just 1 from the R matrix. So basically it said that this diagonal component of monodromy matrix times some creation operator is just again the same order. So it's not commutation relation. To find the commutation relation, actually you need some these two operator to commute whatever the arguments are. But here there's no commutation relation. So integrability already fails. So we relied on the MATLAB or Mathematica or some numerical calculation, and then we found that some quite interesting spectrum, Jordan block spectrum, which I'm going to show you soon. So in these circumstances, the eventual goal of integrability, which is some special form of the integral model like a spin chain, is to diagonalize Hamiltonian, basically, right? Which is quite large size and a systematic way of finding eigenvalues and eigenvectors. But that goal is already from the beginning cannot be realized because Jordan block never can be diagonalized. The best thing you can do is to transform this Hamiltonian into the most closest form of diagonal matrix, which is Jordan normal form. So what are they? Just to review some of that, let's consider certain matrix H, which is a highly degenerate. So that actually, to simplify the situation, let's consider that all eigenvalues are same, but there are many different eigenvectors. So this psi 1j is eigenvector of Hamiltonian with the eigenvalue E. And there can be many, so let's consider them to be gamma. And sometimes this is called, in mathematical literature, geometric multiplicities. Then for each eigenvector, for satisfying this first eigenvector relation, then one can find associated generalized eigenvector, where they vanish only when you apply some number of these H minus E operators. And of course, this M can be increased as many as possible. So total number of this kind of generalized eigenvector and eigenvector is sometimes called algebraic multiplicity, which I'm not going to use. Then one can find Jordan block that starting from some highest vector, we will call top vector, and acting this H minus E successively, then it will reach it to psi 1, which is eigenvector, because if you act H minus E one more time, it's 0. So this is forming Jordan chain, and this Jordan chain converted into matrix form is nothing but just Jordan normal form. Okay? Where all the diagonal element is eigenvalue same as E, but we need one more off-diagonal element which is normalized to be 1. Then what happens in our eclectic model? Actually, if we numerically study this Hamiltonian of eclectic model, then we found that there are certain numbers of Jordan blocks appear with a certain number of multiplicities. Say from N1 to the size capital N1 Jordan block appears small N1 times, and so on. And then for short notation, we'll write down this spectrum as this capital N1 to the N1, capital N2 to the N2, etc., in the some ordering way. And since this pi 1, pi 2, pi 3, using this the fishnet Lagrangian, numbers are preserved, is a good quantum number. So sometimes we'll say LMK sector, where actually this is a Bethe terminology, that L is total size of spin chain, M is the number of Bethe roots in the first level, and K is number of Bethe roots in the nested level. But from just considering 1 to 3s, this L1, which is L minus M, is number of ones in the operator, or pi 1, and M1 is M minus K is number of pi 2, and K is number of pi 3s. They are all preserved. And since, we can already redefine this pi 1, pi 2, pi 3 with another pi 2, pi 3, pi 1, whatever, we will introduce this condition, we will call filling condition. The number of ones is always the largest, and number of twos are second largest, etc. Okay? Otherwise, we can change the definition. And also, we can consider this fishnet version of the model, spin chain model, which we call the hypereclectic model, that this two-parameter cushion to be 0, and only psi 3 is non-zero, which we can normalize to 1. And so this hypereclectic spin chain is just considering P, including only P2, 1 permutation operators. And it's very interesting that actually we found that this hypereclectic model and eclectic model have exactly same Jordan block spectrums, which I'm going to discuss more later. So using this hypereclectic model, we generated this spectrum for example, this m equal 5 and the k equal 1 with a various number of L. And somehow this L equal 18 is some kind of the limit of my desktop computer. And it shows the very strange number of the size of Jordan blocks and the multiplicities. And similarly, some increase, actually in this case decreasing, we considered m equal 4 and k equal 1, and we found also similar sets of the Jordan block spectrum. And one can see there's some kind of thumb rule that how kind of size appears and how kind of multiplicity appears, but it gets really complicated as L increases. So some kind of regularity certainly exists, but we cannot find it. And also here, our numerical calculation is based on k equal 1. But if we increase k to higher, actually we could not do it even numerically. So how to understand this problem? So we'll start with integrability first. As I said, from the beginning, algebra balance did not work, I said. But still, we can use it because we can start with some finite value of q's. And this spin chain is integrable with a finite q. And then after getting this equation, we'll take the limit where q goes to infinite. So this is the result of this finite q case. And the first equation is eigenvalue of transfer matrix. And the second and third equation is the Bethe equation. And the last line is the Bethe vectors in terms of the algebraic ansatz. So using this equation, we'll take now the singular limit where q goes to infinite. So we introduce this parameter epsilon and the psi, and replace it into the Bethe-Ansatz equation. And then the equation themselves have certain factor of epsilon, and which epsilon goes to 0. And this, because of this extra singular factor, we found that the solution of this Bethe-Ansatz equation can be solved analytically, and they are all collapsing into certain same value. For example, this u, which is the first level Bethe root, there are two kinds, the associated with just up to m1 or associated with the second level Bethe root. So this first one is from 1 to m1, and then the second kind of first Bethe root is a k number of them. And this exponent and also this coefficient can be found explicitly here in terms of LMK. And then this finite part of the, coefficient of this epsilon term can be also obtained, where you can see that this coefficient is given by, for example, in terms of this integer nk, and the second Bethe roots are given in terms of the integer in. So since, if you have Bethe-Ansatz equation, there are many kinds of different sets of Bethe-Ansatz solutions. So each solution is just given by choosing this integer sets from nk set or in sets. So for example, if there are the m1 number of uns, then one should choose the n different number of this integer from 1 to L, and that defines one set of the Bethe-Ansatz solutions. Well, unfortunately, this ansatz, scaling ansatz is valid when alpha and beta is positive, but certainly to satisfy beta to be positive, this L should be less than 3m1. So actually, L should be bigger than 3m1. So when L is less than 3m1, this scaling ansatz is not valid. We don't find the solution in that case, unfortunately. But actually, usually the chain size, which is L, is usually much bigger than number of Bethe roots. So actually, those small window is not really the losing interesting cases. So using that, we inserting this back into the transfer matrix eigenvalue. Then we found, first of all, that all the size disappears, completely canceled out. And then, as I said, since we are going to take this limit where not only q goes to infinite, but also we also should rescale this u to epsilon times u bar. So from the eigenvalue equation here, one can notice that since u goes to 0 here, because it's a factor of epsilon, so this eigenvalue is the same as when u equals 0. So in this case, eigenvalue of the transfer matrix is actually same as eigenvalue of t of 0, which is shift operator. So when you shift L times of this spin chain, you go back to the same chain. So all the eigenvalue of the transfer matrix should be Lth root of unity, which you can see from here, that this exponential factor, and they are all integers. So this is just root of unity. So this psi independence already shows some kind of universality. And also, we are interested in, as I said single trace operator. So we'll consider cyclic state only. And this can be obtained when the square bracket is 0 mod L. So one can choose all possible Bethe roots, which can give the square factor to be 0 mod L, which you can count from using some mathematical program, which is very easy to do. On the other hand, this famous Hungarian-born American mathematician George Pólya's formula is entering. Although he said something very humble, this beautiful mathematics will certainly help a lot in theoretical physics. And according to him, basically his so-called enumeration theorem has a much wider applicability. But just to our problem, we'll just simplify the theorem that we want to count all different sets of the necklaces made of the L number of beads, and each bead has a certain number of colors. Here we have 3 colors, 1, 2, 3. How many different kind of necklace can you make? And the best formula derivation I know of is actually done by Spradlin and Bolovich, who are physicists, when they want to compute the partition function of super Yang theory, is that we consider this generating function here, G, where this is trace of all tensor product of these 3 different colors. That means a bead. And the L bead consists the necklace. And this operator L is a counting number of 1 beads in the necklace, and M is a counting number of this blue bead, and the K is counting number of 3 bead. I mean the red bead. But since we should consider only cyclic state, we should include also this projector, cyclic projector, which is the given by this U, which is a shift operator to the power J. And this formula is very useful. For example, let's consider that this trace means that it's a sandwiched with this A1, AL state in both sides. But when, for example, J equal 1, so U is acting on this first state, then it will shift each side. So instead of A1, A2 to AL, it becomes A2, A3 up to A1. And since this state is acting diagonally on these LMK operators, we need to compute this kind of inner product. So the first one is the A1 should be A2, otherwise 0. Second one said A2 should be A3, etc. So actually, this dictates that all the colors should be same. Actually, this is true when J is co-prime to L. And if J and L is not co-prime, for example, if the greatest common divisor of J and L is 2, then you can notice that this color should be same every even side, and independently every odd side they should be same. So number of ones is easy, that just 1 times, for example, in J equal 1 case is L, because there are L number of 1 state. If its state is 2, then it should be 1 times L, because again, number of 2s should be L, because they are all same colors. When J and L is 2, there are 2 different identifications. So total number 1 is L over 2, and the odd side is also L over 2. So it should be just a trace of the square. So one can continue this into J and L to all other numbers, and one can easily write down this generating function into this form. And then one can count also how many different number of integers which have the greatest common divisor with the J and L to be P, which is actually easily understand, because if you divide both sides by P, then J comma L over P should be 1. That means that they should be co-prime. So there is some function which counts the number of co-primes of n, which is less than n, which is a so-called Euler-Tauschant function. So in terms of Euler-Tauschant function, one can write down this generated function into this form, which also can be also summed up partially, such that it can be written in terms of this law. Where this partition function zeta is applying for just single bead state, so it's a trace over x, y, z. So it is just a simple x plus y plus g. So in this xn, yn, jn, it's just replacing xn, yg with xn, yn, zn. So we obtained this generating function, and then if we expand this in terms of number of the x's, I mean ones, and number of twos and number of threes, then the coefficient, which we call d, is a counting number of cyclic states in LMK sector. So we have 2 different ways of solving the problem, and this is the result. So the first column is just we call the naive counting, because just the number of partitions divided by L, because if we just naively thinking that a single rotation is giving same the necklace, so just divide by L blindly. So of course this is absurd. But second column and third column matches exactly that the Bethe answer's result and the Pólya formula is indeed correct. So this confirms that this Bethe answer's equation and its solution is correct, but still, where is Jordan block size? This just counts the so-called algebraic multiplicity, just total size. It does not give any Jordan block spectrum. Also, since we found the Bethe roots, one can use this algebraic balance insert into the creation operators, and can try to see whether there is some eigenvectors. And the result is that actually what we can find is only one vector. So all the eigenvectors of this finitely twisted model is all collapsing together into one vector, which is locked state, which has some very ordered form of these excitations. So first the M1 number of 2's appears, and then the K number of 3's appears all in a row. And this very disappointing result, because since I showed that every Jordan block should have eigenvector, and I showed a lot of eigenvectors. But unfortunately, this algebraic balances give only one eigenvector. And the same conclusion has been obtained by some independent work on these authors using coordinate balances. And online question. Yeah.
Physicist language come to say that Pólya formula counts all possible multitrace operators in UN super n. Pólya formula counts for all possible multitrace operators in UN super n.
Multitrace. Yeah, I think, yeah, that's good. Yeah, one can. Because of this, yeah, actually, I'm going to explain related problem, and maybe he can ask again. But the main difference here is that Pólya formula appears only when the single trace operator is cyclic, right? So multitrace is not cyclic. Yeah, maybe. Yeah. Anyway, anyway, it's not planar limits, right? So. Okay, so so the real question is that all this integrability cannot give the eigenvectors except this trivial one. Although these authors, by the way, found that the generalized eigenvectors, which is associated with this the locked state, which we can find from the Bethe ansatz equation, but they also succeeded to construct the related generalized eigenvector. But real question is the true eigenvectors, because they define the Jordan blocks. So, this leads me to consider this another way of approaching. So first, let's consider take one case, which is only one 3 state, and then there are bunches of 2 state and 1 state. Then let's consider some typical configuration composed of this number of 2's, which is M1, and then there are bunches of 1's, which is L1. Then let's consider the first the 2 state, there is N1 number of 1's, and the second and third is N2 number of 1's, and so on. Then we'll define some very important quantity, which is a lever, we call, is that number of these 1's on each 2 on the right-hand side of each 2. So for example, the first 2, there are N1 of them, and then N2 of them, and until M1 of them. So the first number, for first 2 state has the N1 plus dot 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 and N1 state. And second 2 will have starting from N2. And then the last one is only M1. And all this sum of this N1 plus N2 plus, even including N0, is L1. And then it's easy to notice that when I apply H3, they are always moving each 2 into one step on the right. So this level is always decreasing by 1 unit. And then the maximum number of the state which has a maximum value of the S is the case where all 2's are on the left and as far as possible from 3's, which has this L1 times M1. And the smallest value of S is given by this locked state, which is eigenstate, which we found from the Bethe state, which has a value of 0, because there is nothing, no 1s on the right-hand side of 2's. So it's easy to notice that even from in this configuration, that this anti-locked state is the top vector, and applying all these h's, it goes to until the locked state. And the size of this Jordan block is L1 times M1 plus 1. So this is actually explaining the largest Jordan blocks of this table. But the question is, all this, there are many the Jordan blocks in interior. How to explain that? So to understand this, let's go to some special simple case, which is a 731 sector, which has the maximum value of S to be 8. So starting from this anti-locked state, we act H in arriving this, which already I showed. But you can notice that at the level 6, there are 2 vectors. That means that I can construct some linearly independent state, which I call here A times this state plus B times this state, which can be linearly independent from the 6th state over there, S equals 6th state, such that if we act H, then it will end up to this level 1 with a certain coefficient. And if we demand that the coefficient is 0, then we can find one independent Jordan block, Jordan chains. So imposing this condition, then this one is top vector, and the other one is true eigenvectors. Then one can notice also that level 4, there are 3 vectors. That means that we can consider one more vector, which is linearly independent. So let's call the coefficient to be A prime, B prime, C prime, and acting on H, then we'll have that state. But if we choose this value, then that is 0. In other words, the first vector is eigenvector. So one can notice that if we start the level S, then we can find eigenvector at level S bar, which is S max minus S. And then in that case, the Jordan chain size is this 2S minus S max plus 1, which explains why this 731 has a Jordan spectrum 159. So from this consideration, let's generalize it. So in K-1, actually the most important quantity is number of this dimension of this vector space with the level S. And if they have a dimension is getting bigger than previous one, then we can find the one Jordan chain. So for example, I summarize this table, the 731, and then dimension S was this, which is number of linearly independent vectors. So whenever it jumps 1 unit, we can find the eigenvectors and associate the size of Jordan chains. So the question is that how many kind of independent vectors one can have, which is very well defined mathematical problem, is that actually this dimension S is nothing but number of partitions of integer S into at most M1 parts, and each part cannot be bigger than L1. And it is well known that under the name of Gaussian binomial coefficients, which generate this number. So this q-binomial coefficient, which can be written in terms of product of the ratio of the q numbers, then if we expand this in terms of q's, then coefficient defines this dimension S. And one can easily show that this dimension of S bar, which appears where bottom vector, which is eigenvector, is actually same as the S. Then we can define the generating function, which is this trace over this q to the S minus S max over 2. And then if we have the one Jordan chain, which starts from S to S bar, then inserting into this formula, they contribute just a q number, which is the length of the Jordan blocks. So this generating function, which is the product of ratio of the q numbers, if we rewrite down this formula into the linear sum of the nj q number times small nj, then that is exactly the Jordan spectrum. Okay? So it's all encoded into this q binomials. Then the question is how to generalize this to k larger than 1. So in this case, we need basically this q the factor. So we define now that not only this number of ones or number of twos, etc. We define this s value, and we insert it into a trace formula, and we define this partition function as a bin. Then we are considering that we are considering this kind of a spin chain state as a kind of a necklace where k number of bead, and each bead is not just 1 to 3, but all kind of combinations of 1 to 3s, where only including one 3 state. So this color is not anymore 3, but infinite number of colors, and each color has this kind of all different ways. And since they have 1 and 2 configurations, they will all have different value of s. So we define this partition function, not only number of 1, 2, 3, but also these s values. And it's very easy, since we already computed for a given L and M, we already computed number of s's, which is generated by this q binomial. This bin function can be easily written down in terms of this form, where this g is basically this function. So only difference from the first Pólya formula is that instead of these 3 colors, actually we have infinite number of colors. But otherwise it's all same. So we can use exact derivation as before, this formula. Instead of this L bead, we have this K bead. And each bead has not only 1, 2, 3 color, but all kinds of possible colors with 1, 3 state. Then the result should be same. So the partition function, generated function, is given in terms of this Euler-Toshan function. With instead of the zeta, we should use this bin function. Then we expand this partition, generated function into this number of 1 state and number of 2 state, number of 3 state, arbitrary number of LMK. Then the coefficient is defining this generated function of the Jordan blocks. So it is quite straightforward to obtain the Jordan spectrum for any LMK by just expanding this master formula. For example, it only takes a few seconds to consider, say, A for 2, and then it can be expanded in this form, and that is a Jordan spectrum. And 963 is a different form, of course. Okay, so since I said that this hypereclectic and eclectic model have the same Jordan block spectrum, one should understand why. And let's consider that the eclectic Hamiltonian, which is composed of these 3 different kinds of permutation operator. And then one can notice that this level S is also playing important role here, that H3 is just decreased by 1 unit, but H2 decreased by M1 unit. M1 is number of 2 state, or H1 is actually decreasing S value by L1 unit. So already one can notice that if the S bar, where eigenvector appears, is smaller than M1, then acting H2, H1, it just kills it. So naturally, eigenvector of the hypereclectic model is the eigenvector of the eclectic model. So it's very simple. So the question is, what happens if S1, S bar is not smaller than M1? We have some kind of abstract formalism, but just to see what's going on clearly, let's consider some examples, 731 again. And then we already showed that there is eigenvector, which is given by this -9 times this plus 5 times that vector, which has been killed by acting H3 5 times. So what happens if we act the H 5 times? Then we notice that we just add certain sub-leading vectors with a low value of S, and then just find the coefficient. And if the coefficient is a 3 psi 2, then that's it. So this proves that we can, if we find the eigenvector of the hypereclectic models, then one can always find the eigenvector of the eclectic models by adding certain sub-leading terms. And they don't change any Jordan block structure. That's a kind of conceptual proof of the universality. Of course, we cannot do it all case by case because M1 and R1 is integers, and there are all different kind of property. Then it's very difficult to do it in general way. But that is just the physics proof. Okay, so this leads me to the summary and some future directions. So we basically claim that this eclectic or hypereclectic spin chain model, which has been constructed from R matrix, which satisfies Yang-Baxter equation, we cannot solve it using Bethe ansatz because they develop Jordan blocks. So the integral model is unsolvable by integrability technique. Instead, we need to use some kind of a mathematics to find it. And we show that two applications of Jordan formula to solve possible Bethe ansatz equation and to find the generally k larger than 1 spin chains. And well, there will be many applications, I guess, because already I heard that several different talks on correlation functions of the fishnet model here. And since they developed Jordan blocks, it is not anymore usual conformal field theory. It should be logarithmic conformal field theory. And the correlation function should have certain logarithmic dependence. I don't know what's the meaning of it to the correlation function here, the authors are considering, but certainly they should exist. And of course, we have a kind of assumptions which I have not really addressed, but well, its mathematical proof will be quite interesting, such as, for example, universality conjecture. And also, one can try to apply our Pólya formula to other kind of non-Hermitian spin chain, which can develop Jordan blocks. Also, eventually, the Bethe ansatz is not only providing eigenvalues, but also it wants to give the eigenvectors. Here, we showed how to find the Jordan block spectrum, but each Jordan block should have eigenvector, but it's not clear what is the eigenvector is. For example, let's consider this 10, 5, 1, and it has this rather simple Jordan block Jordan spectrum. But its eigenvector is much more complicated. For example, the coefficient is some special integers. And the question is is there any algebraic way to find this eigenvector systematically, which is still we don't understand completely. Okay, so I think this is what I want to talk. Thank you very much.
Questions?
Thank you very much for the nice talk. Do you think there might be a hidden symmetry behind this structure of the Jordan blocks, or like
hidden symmetry?
Yeah, because there are examples of Hamiltonian with this kind of Jordan block spectrum, and there is some I don't know, GL11 for the case of UQ of SL2 at Q root of unity, or
that's
that's
a good question, which I have not thought much. But actually, I already explained that it's a highly degenerate spin chain, right? All eigenvalues are all same. That means already there are huge amount of symmetries.
Yeah, I see. We are seeing some spin chain with Jordan blocks of size. So if you have length 2L of the spin chain, we get Jordan blocks of size L plus 1, but yours are much bigger than that, I think. So in our model, we suspect there is some hidden symmetry.
I see. That
underlying,
when
yeah.
L is quite large, you mean? As L increases,
Yeah,
what's the scaling of the...
yeah. It's linear.
That's a
For
very
you,
good question.
is it linear or it's polynomial with higher?
Yeah. Good. Yes. Actually, we have not thought about that. Also, but of course, this everything is in terms of q numbers. That means that there should be some kind of hidden quantum group symmetry. Which we cannot figure out exactly, but certainly there should exist.
So your q numbers are q is what in your case?
Q is just arbitrary kind of what do you say, like XYZ. You can just introduce certain fugacity into the partition function. So there is no physical meaning itself. But this Q is different from other XYZ in the sense that it appeared in terms of the Q number. So I mean, some kind of quantum group symmetry may exist.
Yeah, so also I was thinking about Fabricius-McCoy, the symmetry, the hidden symmetry of Fabricius-McCoy, which appears in the XXZ at Q root of unity. There is some loop algebra behind behind the spectrum, and I think the usual Bethe ansatz fails for that that case.
But this Q is actually different in our case because our model is rational from the beginning. There is no Hamiltonian doesn't include any.
But sometimes there are miracles. Some q-deformed model becomes some isotropic model when q is root of unity. So I don't know. Okay.
Anyway, thank you for your question.
There's a question here, maybe.
So just first few remarks. So when we computed spectrum of super-Young mills, so we of course have to use Pólya formula. And we, of course, checked consistency of Bethe ansatz equation with zero momentum, like for ridiculously many things explicitly. This was part of the job, of course, and we solved SUN for n, it was, but it was like part of, not even sanity. We just had to claim full spectrum. So we actually honestly did the job for, and my methods include not only PC224, but because of some dualities, actually go to SU 14 or something on the way. So just as a comment, but it was not non-twisted system. Yours is twisted, so it's not like honestly the same system, but of course it's very related. So the second point is about this diagonalization using counting using Bethe equations. So it's, I mean, we know by now that Bethe equations, Bethe ansatz is complete if you interpret properly. And this actually means that whenever you have Jordan blocks, which correspond to diagonalization not only of Hamiltonian, but of all conserved charges simultaneously. No, you cannot just diagonalize it with Jordan and Jordanize. So if you care about all conserved charges simultaneously, that it's impossible to have two Jordan blocks with the same eigenvalue. This is immediate concept.
Jordan blocks with what?
With the same eigenvalue.
Same eigenvalue.
So if you care about all conserved charges, not only Hamiltonian, that's a theorem, mathematically rigorous, that not for twisted limit, but before you take the limit. But that's what you did. You first computed and then took the limit.
Yeah.
So if you care about all conserved charges simultaneously, this is a theorem that it's impossible to have two eigenvectors which share the same common eigenvalue of all conserved charges. It's impossible. It's equivalent to completeness. I mean, this is the same thing actually.
I see.
So, but I mean.
But our case is a singular case.
No. You consider a regular case and then you take singular limit, right? So you have the generation in the spectrum of Jordan blocks because you consider only one conserved charges, which is Hamiltonian. So my first question is, why is this Hamiltonian? I mean, integrable model is the point of that we have collection. So, I mean, what distinguishes this one to consider?
It's physically interesting. I mean, it's a dilatation operator.
What something else? Not yet. Yeah.
Do you want to comment on the higher charges? I mean,
On this model.
I mean, yeah, they are not the same.
Yeah, it's not because actually it's a quite singular transform matrix. R matrix itself is quite singular, so the construction of charge is not as rather different if you mod expand of this transform matrix.
I mean, you're right that you cannot find like you can if you bring like Hamiltonian in Jordan form, then in this basis the other ones are not in Jordan form. That's what you meant, right? And in fact, if you take transform matrix, you can also bring it in Jordan form, but then as opposed to diagonalizable case, basically the similarity transform will involve the spectral parameter.
And if it's a transform Ahn,
Yeah.
you have single Jordan form.
Single, yeah, but basically, anyways, the statement of there's a statement theorem of simultaneous diagonalization of higher charges in diagonalizable case, but you cannot simultaneously bring all the charges Q into a simultaneous Jordan form.
No, of course not.
Well, it's not so. Of course, it's actually a little bit non-trivial, but anyway, yeah, we focused on Hamiltonian because of dilatation operator interpretation.
So, as far as I understood, this eclectic chain is sort of a first-order perturbation theory of
That's right.
of fishnet. Then my question is, can you really construct states? You said that there was difficult to construct the states, but in our old paper with Korchemsky, Gromov, Sizov, Negro, we went to the second order to see the logarithmic behavior.
Second order in G?
Hmm?
Second order in
Yeah, to second order.
in lambda.
First order was not enough, but second order was enough to construct the states and to construct then the correlator which has this logarithmic behavior, etc. So is it hidden somewhere here in your formalism, this kind of, can you demonstrate the logarithmic behavior of underlying conformal?
Yeah, I mean, if you have a Jordan block, then you should have the logarithmic correlation function.
So strangely enough, we needed really second order to see.
Yeah, so okay, so
to see it.
what happened in first order?
Sort of, I forgot a little bit the details. I'm looking at it, but it's you try to build the renormalization of the full set of operators.
But in the
semantic equation.
I'm not familiar with this Fishner limit, but in the lambda square order, but still the Lagrangian contains the leading orders of Q's, right? The deformation parameter. How do you define this? The double scale limit?
Yes. And then at least you can construct all the states and construct the renormalization of operators, count semantic memory.
So it appears only from the second order.
Yeah, you needed it. Otherwise, it's not closed. The equations are not closed. So I wonder whether.
So I don't know whether Jordan block structure should appear. I'm sure that they will in the second order too. But certainly in the first order there is Jordan blocks, and the question is why they don't contribute to logarithmic form of the correlation function. That's it depends on, of course, operator, which operator you are considering correlation function. So if we are considering this SU3 sector, pi 1, pi 2, pi 3 only.
It was just 5-state spin chain, and we considered all possible graphs of which renormalized the spins, but
yeah,
you can't avoid the second order if you do this computation.
Maybe we can discuss later.
Okay.
Oh, so it's different sector. It's not pi 1, pi 2, pi 3 sectors?
I mean, the point is that this is not exactly fishnet. I mean, in fishnet, you always say that the other fields decouple. So the phi 3 field decouples. But of course, if it decouples in the sense of interaction, but if you keep it inside the trace, it doesn't decouple. And that's the beauty here. You put these walls into the fishnet. It's like fishnet plus walls. And that sense is a slightly different problem. Anyway, Pólya also had a question.
So, but if you forget about phi 3, so there is still a question with phi 1, phi 2 only, that it seems some of the states, they remain having 0 anomalous dimension to all orders, and some states, they get dynamical. So can you say anything about counting of those states which are protected at finite lambda?
So operator containing only pi 1 and pi 2?
Yeah, only phi 1, phi 2. Can you do counting at finite coupling of states which are protected?
That case is diagonalizable, right? I mean,
if you have only pi 1, pi 2, there's no Jordan block.
If you have only phi 1s and phi 2s, it's diagonalizable, except if you start putting derivatives.
This existence of pi 3 is playing the very fundamental role.
Anyway, I think we should, we should probably, maybe a last question from, so you get, in fishnet, you get Jordan blocks once you couple derivatives into it, but phi 1 and phi 2 by itself is actually happens to be diagonalizable, even though it's non-Hermitian. So Dima, you had...
Well, I mean, there is a lot of similarities of what you're saying with crystal limit. I mean, crystal limit is not this singular twist limit. It is limit when Q, not your Q, but Q of XXZ deformation goes to infinity. It's called crystal limit. There are Cashevara bases, box ball systems, which have kinks, propagation rules similar to yours, but not exactly the same. Partition functions with another Q which you use. Counting of strings using KKT bijection. All these words, did you compare what you're doing with this combination? I mean, because it's a lot of, I don't say it's the same, but it's very like many similarities with this story. Okay.
I think we should proceed, but before doing so, let's thank Changrim one more time.
Thank you.